Hello everyone, I'm Joe. Today let's continue to learn the binary arithmetics, and I will also talk a little bit about binary codes. First, since whenever we talk about the signed binary number, we have to specify how many bits it has, right? Then which means there's always a upper and lower limit for the given signed number. So for a given n-bit signed binary, the largest positive number should equal to 2 to the power of n minus 1, then minus 1. For example, for a 4-bit signed binary, the biggest positive number we can write is 0, 1, 1, 1, because the first bit has to represent the sign bit. And the magnitude of this number is 7. So the largest positive number is 7. For an 8-bit, we can write 0 with 7 ones after that. If you convert this to decimal number, that's positive 127. Okay. Similarly, for 16-bit, we will get positive 32,767. However, the largest negative number, largest here means the absolute value, the largest absolute value, okay? So the largest negative number equal to negative 2 to the power of n minus 1. So you see there's a little difference between the negative number and the positive. Why is that? Let's take a look using an example. Say we have a 4-bit signed binary, and we already know that if we list all of them, we get totally 16 numbers, 16 different combinations, right? And starting from 0, the upper half will stand for the positive numbers, and the largest 0, 1, 1, 1. Okay, and so if we find the corresponding negative number for each positive number here, we will match them. So positive 1, negative 1, positive 2, negative 2, positive 3, 4, 5, 6, 7. Okay, what you will find is that we have one number is left out. And in this case, it's 1, 0, 0, 0. If we take 2's complement of this number, remember how to take 2's complement? First, we do 1's complement, 0, 1, 1, 1. Basically, you flip every bit, then plus 1. You will get what? So you will find for this number, the 2's complement is itself. And so and because this sign bit is 1, so this gotta be a negative number, and its magnitude equal to 8. So it's negative 8. Okay, so this happens to any other n-bit signed numbers. Okay, there are always one more negative number than the positive numbers. So give you the 3 example here. For the 4-bit, the 4 range is from negative 8 to positive 7. For an 8-bit, the range is from negative 128 to positive 127. Okay. Since any n-bit signed number has a specific range, then there is a possibility that for some operation, either addition or difference, the result might go beyond that range. And if that happens, we say that we have a sign bit overflow. Basically, we found there's some abnormal status on the sign bit. Let's take a look. For example, if we have an 8-bit side number add together, 75 plus 96, we know it's equal to 171, right? So let's do this in the binary number, 8-bit size binary. So 75 can be represented as 64 plus 8, that's 72, then plus 3. Okay, so this is a 7-bit, then we add a 0 here, make it 8-bit, and the 96 equal to 64 plus 32. So let's add them together. 1 1 0 1 0 1 0 1. So the result equal to this, and we can see that I got two positive number added together. Just check the sign bit here. 0 0 both means positive, but their sum becomes negative. So that's what happened when we have a sign bit overflow. Basically means the resulting sign bit is flipped. It's wrong. Okay. And apparently this number is a negative number. It's not 171, right? Similarly, if we do a subtraction, like negative 80 plus negative 65. So if you remember how we do this, we write both negative number into 2's complement form, right? For 80, we got 64 plus 16. Put a 0 here. Take 1's complement. 1 0 1 0 1 1 1 1 plus 1. Get 0 0 0 0 1 1 0 1. So this number is representing negative 80. For 65, we have, for positive, we have 64 plus 1. Then take 1's complement form. 1 0 1 1 1 1 0 plus 1. We get 1 1 1 1 1 0 1. Okay, so this represents negative 65. Then we add them together. So we got 1 1 1 1 0 1 1 0 1. So take the extra bit out, so the result equal to that. Now we see we have two negative number. Their sum should be a negative number, but we are getting a positive sign bit here. So the sign bit flip again. So that's why we call this sign bit overflow. So whenever sign bit overflow happens, we know the result can go beyond the range of that sign number. Here is a summary about sign bit overflow. First, when to check. As we see the example in the previous slide, if the two operands have different size, then we don't need to check overflow, because positive plus negative, the results are always smaller, it won't go beyond. However, if the two operands have the same sign, like positive plus positive or negative plus negative, then we must check for overflow. And how to check? From math point of view, check if the result is going beyond the range of the n-bit sign number, right? Just check if it go beyond the maximum positive or the maximum or the largest negative number. But from circuit point of view, it's much easier to check. Just check if the sign bit is flipped after the operation. If I have two positive numbers, then I get a negative number, then sign bit overflow happens. And how to prevent it? Basically, you have to make sure the sum of your numbers still stay within the range. This range we talked about before. Okay, we have talked enough for binary addition or arithmetics. Now let's talk about hexadecimal arithmetics. So how to add and subtract hexadecimal numbers. I think the only trick is that we have to put a carry whenever the value getting to 16, right? Because we have no letter or number to represent 16. We have to carry. So let's try this. 6b3 plus 49c. Okay? So just do it like the binary addition and the decimal addition, except that we are using the hexadecimal number. So 3 plus c, basically c equivalent to 12. So 3 plus 12 equal to 15, and we have a letter to represent 15, which is f, right? So no carry here. Then b plus 9. B is 11. 11 plus 9, we get 20. And we know that we have to carry for every 16. So 20, we need to carry 1 to the next bit, and then we have 4 left here on this bit, right? Then 6 plus 4 plus 1, we get the 11, which is letter B. So the result is B for H, or B for F, sorry. For subtraction, we can subtract directly, but we can also do the 16th complement and then addition. Okay, so basically we need first take 49c here. Okay, then we use the number with all f's to subtract this. So we get f minus c. F is 15. 15 minus 12, we get 3 here. Then 15 minus 9, we get 6. 15 minus 4, we get 11, which is B. So this operation becomes 6b3 plus b6. Oh, sorry, I missed one. So this is called 15th complement. We need to add one. So b64. This is the 16th complement. So actually we should add b64, not 3 here. So 3 plus 4 we got 7. B plus 6 we got 17. So we need a carry and the left one here. So 6 plus b, that's 17, 18. Again, we need a carry, and then we have 2 here. And we take out the extra bit here. So the result is 1217, but in hexadecimal, it's not a decimal. Be careful. Okay. Next, let's talk about some basics about numeric code. So there is essential difference between a code and a number. Okay. A number has magnitude. We can compare two numbers. But a code is just a systematic and standard use of a given set of symbols for representing information. If we use the binary number as symbols, we got binary code. Code doesn't have magnitude. You cannot compare to code. But the code contains information. One good example is the traffic light. To some level, the traffic light is one type of code because the different color tell us different information. Okay, and for binary, we have different code system, and the most commonly used one is the binary coded decimal system. And there are different kind of BCD code. The most commonly used one is 8421 code. Basically, it uses four binary digits or a 4-bit binary number to represent some information. Okay, in here, the information is a decimal number. You can think we can encrypt a decimal number into 4-bit of binary. Okay, you must know this binary number, then you can translate it to the corresponding decimal value. Okay, and here is how to calculate this. So B here stands for the bit. B3 is MSB, B0 is LSB. So the MSB has a weight of 8, the LSB has a weight of 1. Okay, so that's how you calculate. And there's another type of BCD code is called 6311 code. Basically, just change the weight of each bit. That's how you calculate it. And we have XS3 code. Basically, it's equal to 8421 code plus S3. And we have 2 out of 5 code. In this code, 2 out of 5 bits are 1. So we have 2 ones in the 5 bits. And finally, gray code. That's the code for successive decimal digits differ in exactly 1 bit. If you remember, we used this type of code when we are talking about column map. The column map is formed using this strategy. Okay. And here is a table to showing the representation of decimal digit 0 to 9 using different code system. Okay. For BCD, we can find the decimal value and the binary value, they are kind of match, right? But for 6311, they are not, because they are coded using this formula here. Similar thing happened to XS3 code, 2 out of 5 code, and the gray code. Unless you know this how this code works, you won't find out the true value it represents. Okay. So now let's try this. Try to write the numeric code with different coding system and see what's the difference. Okay. But first, let's try to write it in binary number. So 87 in binary, we will write as 64 plus 16. That's 80 and plus 7. So this number, this is a 7-bit binary, represent 87 in decimal. Okay, that's the true value of this number. But now, if we want to write this number using 8421 code, basically we won't treat this as 87. We just treat it as two numbers, 8 and 7. Like I said, there's no magnitude. There's no like tens, ones bit, tens bit. No such a thing. It's a code. Just represent the number. So for 8, if we look it up, that's 1 0 0 0. For 7, that's 0 1 1 1. So if we want to write 87 in BCD in 8421 code, that's it. So this one stands for 8, this one stands for 7. Similarly, if we're using 6311 code, we will get 1011 and 1001. For XS3 code, we will get 1011 and 1010. If you check here. For 2 out of 5 code, we will get 10100, 10010. Finally, using grain code, we will get 1001, 1011. The last code system I want to talk about is the ASCII code. The full name is American Standard Code for Information Interchange. This is the kind of standard code system used in different data processing systems, including computer and the internet. It's a way to store and transfer the keyboard information, like the letter keys, number keys, and special keys. Okay, so whenever we type some key in the keyboard, the signal will be converted to this type of code, then sent to the processing unit to be processed. Okay. So it's pretty simple to use this code. We just need to look at the table here. So this table has x-axis 0 to 7, y-axis 0 to f. So basically each letter or each number or each special key will be represented using a 7-bit binary number, okay, or 2-bit hexadecimal number. So to find the corresponding the code, sorry, I shouldn't say number. To find the corresponding code, we just for a specific letter or key, whatever, we just need to look up the x-axis and the y-axis. Okay, so both axes in this table are written in hexadecimal number. Actually, for the x-axis, you can also think it's written in octal number because there's only 0 to 7. Okay, but it doesn't matter much. For example, the uppercase M, as shown here, if we are looking for the M, which is here, so we found the x-axis is 4, y-axis is D, so the code for M is 4D. If you convert them into binary, you get 0100, 1101. Okay, 2-bit hexadecimal or 8-bit binary, but basically 7-bit. Yeah, because the highest bit here, level V1, the maximum is 7. Okay, now let's try a example here. So let's try to encode a string like binary is found into ASCII code. So that's basically what happened when we type in this sentence or phrase. Okay, it will be converted into ASCII code, then send it into the computer. Okay, so we have to find the code for each letter here. Here we don't include the quotation sign. So the code is B, small b. So we look B. So we got 6, 2. For I, let's find a small I, which is 6, 9. For small n, that's 6, E. And small a, that's 6, 1. Small r, that's 7, 2. Small y, that's 7, 9. And the space is here, that's 2, 0. Then we have small I again, which is 6, 9. Small s, 7, 3. And the space again, that's 2, 0. And the small f, that's 6, 6. Small u, 7, 5. And the last one, small n, 6, E. So basically when we type in binary is found on the keyboard, the computer will receive this code. Okay, so it knows while typing binary is fun. Okay, hope you enjoy today's video. I'll see you next time. Thanks.